Okay, so here's the summary of what we've got. Our derivative, you're thinking rate of change, or derivative, you're thinking slope, tangent line, slope of any point along the graph. So when I say derivative, you're thinking
rate or slope.
Bingo, rate or slope. Okay, we are going to look at gravity before we close this section. We're going to look at derivatives as slopes more later, but we're going to finish looking at them as rates now, using some of the most important rate functions that Isaac Newton gave to us in his Principia. So here are the functions for gravity. These all relate to motion. If you ever take physics, what color do I want to use? Let's use blue. If you ever take physics, these will be really important functions you would use all the time to represent motion. But we have A of t. I've already set up this bracket so I can just fill it in, but you'll want to write down all these parts. A of t equals negative 9.8 meters per second squared. And as your A of t, if you do a capital A, that's also fine. Velocity in the metric system is measured as negative 9.8 t plus v naught. This is pronounced v naught. It's like a subscript 0. So you could say v sub 0, but in math we say v naught. Not as in like N-A-U-G-H-T, as in you have nothing. And then h of t is our position function, and that is measured as negative 4.9 t squared plus v naught t plus h naught. V naught is your initial velocity.
Why is position h of t?
Because it is your initial height or position.
Ooh.
Okay, and then here are, if you're using feet, if you're in our stupid American system, then you're going to want to use different measurements. A of t is negative 32 feet per second squared. B of t, negative 32 t plus v naught. H of t is negative 16 t squared plus v naught times t plus h naught. Now, I actually just have these memorized because all I need to actually remember is 2 of them, and later you're going to figure out how to derive them, literally. You're going to be able to get one from the others. So we'll learn that in the coming weeks, but for now, you'll just have to take these functions as they are. The major assumption with these functions is that we're assuming the only thing acting on an object in free fall is gravity, because we're forgetting about air drag, we're forgetting about any interferences that may occur. We're forgetting about all that. We're just going to assume that gravity is the only thing operating on the object with these functions. If you add into account things like drag or other interferences, you would have to have a far more complicated equation. So we're just assuming that this is the only thing operating on those. Notice some of the similarities and differences. The main difference is just the coefficients, because they're just measured differently between the metric system and our imperial system. So the 9.8 meters per second corresponds with the negative 32 feet per second squared. But like V naught and H naught show up in the same way. The formulas have a similar structure where it's a constant and then it's linear and then it's got a squared term, or a parabola. But okay, So I have some problems for us to solve. Example 1, the height of a ball in feet t seconds after it is thrown is given by h of t equals negative 16t squared plus 38t plus 74. Its upward velocity is given by v of t equals negative 32t plus 38. From what height was the ball thrown?
It's h of o, so
H, how do you say that?
h naught.
H naught.
Should be
74.
Yeah, so from what height was it thrown?
74
74
feet.
74
feet.
Good, okay. What was the ball's initial velocity?
VO.
38.
Feet per minute, second.
38.
38 feet per minute, second?
Feet per second.
Okay.
Yeah.
Was the ball thrown up or down? This is the question, it's not on here. With the initial velocity, or did you throw the ball down or did you throw the ball up?
Up, because it's a positive height.
There you go. Because it's positive, we threw the ball up.
Yes.
Also, it's defined as upward velocity. So if I had defined it as downward velocity and then gave you positive 38 feet per second, you'd have to think backwards, but you would be throwing it
Down.
Yeah. So if I had defined it differently. Okay? Was the ball going up or down at time t equals 2?
Position.
Let's talk about how could we find that.
So we find position.
We want to know if it was going up or if it was going down. Hi,
Grab some music stands out here.
you're all good. We want to know if it's going up or
Velocity at a
down.
certain point. See if it's
Yeah, we
positive
want to
or
know the
negative.
velocity.
So plug 2 into that second formula and look and see if it's positive or negative.
That's right.
And it would be negative.
Can you scroll back up to the imperial? I think I.
Yep.
VT minus
Read
32. T. Okay, never mind. I have it.
Okay. Okay. So, yep, we're gonna plug 2 into velocity. It will be negative, so we know that it's
Yep.
going.
What's
Yeah.
T?
T is time
Okay.
in seconds. That is defined right here. T seconds after it's thrown. So am I going up or down?
Down.
Oh, definitely.
Go ahead and graph h of t. The way I was looking for my phone to check the time, but it's right there.
Seriously, this
Mm,
32. Oh wait, that's time.
I'm changing my window so I can see it better. But that's what I saw originally.
Go ahead and put your window as this. Put your window as that.
There we go.
Got it? Yeah.
And what?
So there you go. There's our nice little graph of
You're
the
missing the
situation.
plus 74.
It's not plus 38.
plus 74.
It's 38x.
This should be your equation.
Yeah, negative 16x squared.
Oh, I thought you just completely wrong.
Oh, did you do B and T?
Yeah, you remember the second one.
That won't do it. Okay, so here we are. So let's just talk about some of the parts of this. So where's that y-intercept? No, you should just know.
Oh, 78 or 74, whatever the function was.
74. We could trace it.
74.
Yeah, you could use your calculator and trace it. It is 74.
It's 74.
Yeah.
I just traced it.
Great.
Just checking you.
Okay,
Making
good.
sure you aren't lying to me.
Okay. Hey, that's good, you know. Always gotta fact check me.
Yeah.
I do a lot of wrong things on the board. So, so 74. And why does it look like this? Why is it the shape?
As x okay, I get so as x is getting closer and closer to 0, so because the negative 16x, the 16x squared is negative.
Okay. Why is that significant that it's negative?
Because it's an x squared, so it's a parabola, but
Yeah.
putting the negative there flips it.
Good. X squared is a parabola. Making it negative flips it
On its head.
Vertically.
vertically or over the x-axis, you can say too. Okay, good. So because it's a negative x squared function, that's why it has this shape. So if you took the negative out, you'd flip it, and then it wouldn't even represent the height of this ball at all. But so there it is. Okay, so now my question is, actually, go ahead and hit trace and make sure you're on the function, and then find at time 2. Because we were asking, does the ball go up or down at time 2?
It's
Yeah.
going down.
How can you tell from this? What does this graph represent?
This the curve, the height of the ball too. Throwing it up. It's going up.
Yeah, the height of the ball.
Right.
Could we quite literally imagine that the ball is
That's
traveling
what it
this
looks like
path?
when
On
you
the
chuck
line, yeah.
something up there.
Yeah.
Mhm.
I mean, you could just imagine the ball is literally traveling
If you
this
actually have a
path
decent
in
arm.
reality.
Yeah. Just gotta absolutely chuck.
If you're just watching somebody like lob a tennis ball, it's just gonna follow the blue line. Okay? So we know it's going down because it's past the maximum point.
Yeah.
Right? Okay. So I'll show you the next questions. At what time did the ball reach maximum height? How high was it?
92.4 was the max height, and 1.7.
Why do you think that, and how do you know?
I did the trace,
Okay.
and if you trace, you can go to the maximum of your graph.
Are you convinced that you're at the maximum? What if you're just a little to the right?
It pops up with a big yellow thing that says maximum, so kind of believe it. But
Kind of you're stupid.
It's
If
a
you
special
were-
calculator.
to think about it,
Yeah, because mine doesn't follow that close.
It's not 92 feet, so it's wrong.
It's close
92.4.
to 90.
It's not 92.4 either.
Close to 96.6.
Okay, how do you know
Well,
that?
yeah.
By the trace, that's.
Oh my
It's
gosh.
close to that.
So you used trace.
I don't know for sure.
Did you do second calc? And then use
No,
this
I
function?
just was looking at it.
Oh, just
Yeah,
off the cuff guessing.
Yeah.
So this is even
If I did-
worse.
that, then you can plug it in and it takes
Okay,
you.
so second calc and then do 4 for maximum.
Yep.
And then now it's going to ask you left bound. So go to the left of where you know the maximum is, or at least where you want to find the maximum. So as long as you're left of it, you're good. Hit enter, and then it's going to say right bound. and then you're gonna go to the right
Oh,
of
that
where
makes
the
sense.
maximum should be. And then it says guess. You don't have to do anything, just hit enter. And then it'll tell you the maximum.
Yeah.
Okay,
I
96.56.
got
The right value.
Yeah, I had accidentally put a point on it, and I was reading my point that I put was at 90.
Interesting.
Not the maximum.
Okay. So, at what time did the ball reach max height?
1.18 seconds or 19.
1.187
Yeah.
seconds. Usually with calculus, you go to 4 decimal places. So we'll do 1.1875. How high was it?
96.562.
There you go. So then we can write this as a point, actually. So we can say
That's
1.1875.
So,
We can remember that seconds. 96.5625.
That's an arm.
That's up there.
10 stories is, 96.
We started 74 feet in the air. So
Oh,
we really
yeah.
threw it up 22
Right.
feet.
Okay, that's not bad.
It's like a story and 3/4 of the story.
Yeah, so you're like starting on like whatever story and then you're like
Yeah.
allowing the
Seventh,
finish ball.
yeah.
Yeah. How long was the ball in the air?
Ooh.
That would be where it crosses the x-axis.
So, what do you think? Do you think we can just move our cursor over and find that value?
74. Oh, wait, no, that's.
Okay, here's another little
There's
function.
a 0.
Oop. Second calc. Number 2. It's going to ask you the same question. Left bound?
Yep.
So go to the left of where the 0 should be. Apparently I can't press and hold on this. I can press and hold on my physical calculator. Okay, left enough. And then right bound. That's right enough. Guess, enter. Where is our 0 at? In other words, how long was the ball in the air?
So 3.6 seconds. 3.6442 seconds.
Yep, so we'll do, we'll say that t is approximately 3.6442 seconds.
When you went to the other thing, the y value said, on yours said -1 e to -11. Mine says -2 e -11. And that one says 1 e negative. What's the difference?
1
What
e
does
to the
that mean?
negative 11, yours says 2 e to the negative 11?
Mine says -2 e to.
Negative 2 e to the negative 11?
Yeah.
It's guesstimating. So
Okay.
it's like, what should y be?
0.
0. So it's wrong.
Yeah.
Your calculator's wrong. Both of ours. It's giving us the close enough that it can compute.
Okay.
So this number is tiny. To the negative 11 is something very small.
Right.
So it doesn't really matter if you have -2 or I have 1 because it's just going to be basically
Basically
0.
Okay.
So yours just ended up estimating a little bit under the x-axis.
Mhm.
Mine estimated a little bit over the
Yeah.
x-axis. That may have occurred because we might have hit our bounds slightly differently.
Mhm.
Like the left bound, right bound.
Yeah. That makes sense.
But we don't have to worry about it because we know it should be 0.
Right.
That's a good question. All right, we got one more example. Cowboy Stadium. The monster TV at Cowboy Stadium is 90 feet above the field. This is real life. You gotta look this up. Could a QB stand directly below and throw the ball straight up and hit it?
Oh, I'm gonna go with yeah. I believe in Dick.
Okay, I have to give you some assumptions.
Yeah.
Such a sick name.
Gravity is our only force. I'll also give you that your average QB, your high average QB, has an initial velocity and an initial throwing velocity of 45 miles per hour. I'll also tell you that your average QB has your average height of about 6.5 feet. That's being kind to like Aaron Rodgers. Okay, this is all you get.
So, he has to throw it 80. 3.5 feet. Wait, so we're trying to find position.
Can a QB hit the monster TV?
So we would use.
I mean, this is kind of concerning. What if in the middle of the game he threw it high enough and the monster TV messed up his Hail Mary?
That would be horrible.
We would be using the position, right?
Would you use position or would you use height? Right? So you have your
Position and
initial-
height are the same thing.
Or yeah, I
It's
guess yeah, it's
context.
position.
Yeah.
Yeah.
We just call it
So,
HFT,
yes.
but that's
So,
position.
HFT. And then you just put all those things in.
But we don't have time.
I think you have to find time, I guess. Because the HFT equals 90.
How do you?
Because that's the ultimate, right?
So we have the velocity.
Yeah.
And we have.
Initial velocity, initial height.
Do you have the real time on the top? Like, you have a watch?
No.
No.
They took watches
We
away
have
from
like 30
us.
seconds, I think.
Oh.
We'll finish this on Monday. But keep thinking.
Just trying to figure out which equation to use.
Which equation to use? What equations do you have? I didn't
Well,
give you any.
We wouldn't use velocity because we already have.
Yeah,
velocity.
we have velocity.
Okay. What is velocity?
45.
Our initial velocity is 45, but it would slow down with gravity as it goes up, right?
So it's got, yeah, that ball's not going 45 miles per hour
The whole way
time. That'd be quite the impact for the wide receiver.
Yeah. So you would use acceleration?
Deceleration.
Or, well, yeah, it would be deceleration.
Negative
But you use the
acceleration.
acceleration. Something like that.
I think you would use negative
Well-
acceleration, and you would use position.
Come on in.
So wait, would you find the time first, and then because acceleration is in feet per second squared, then you can calculate how fast it is, or like what the deceleration would be. Did you do that?
So it's not going to go 45 miles per hour to the end of the time.
Right.
What should we use to model its velocity as its...
Oh, the graph.
Graph what? 45?
Wait, what?
You could.
Wait, yes. You could use. Initial velocity would be 45. You'd plug that into the velocity one, so you'd do 9.8 t plus initial velocity. Oh, but what's the time?
Are we in metric or imperial?
Imperial.
Sorry, negative 32 t plus initial velocity.
Are you recording? Yeah, because Jonah's gone. Is it a video? Yeah.
Go to Jonah.
Go for it, Lori. Hi, Jonah.
There's like a live stream.
That's what I mean.
I'll see how people velocity is.
I could just do that to you too, but I'll just upload this
You're
video.
gonna put it on YouTube?
Yeah. I've recorded many of our classes on YouTube.
My digital footprint.
So we can build a DFT function.
Did you build a HFT function as well? Because you know your starting height and your.
Yeah, we could try it.
Well, I couldn't even pull in.
Okay, go ahead and stop the recording, but we'll pick it up on Monday. So you